Hi viewers, let us see the counter design. So in this counter design, we are going to see how to design a different synchronous counter by using mod 6 or mod 12, mod 5 counter. This is a sequential circuit. So for this we have to follow certain steps to design this counter. So first step, obtain the transition table from the given circuit information and determine the number of flip-flops are required. After that, we have to choose which type of flip-flops to be used for designing. And from the transition table, we can derive the circuit excitation table. And by using different K-map or any other simplification method, we can derive the circuit and the flip-flop input functions. Finally, we can draw the logic diagram. So in this we have a question. So first question is design a synchronous mod 6 counter using clocked JK flip-flop. So in this question itself detailed they mentioned JK flip-flop. So we have to design the synchronous mod 6 counter using JK flip-flop. Next we have to find how many number of flip-flops are essential to design this synchronous mod 6 counter. So that should be followed in this step 1. So step 1 is used to determine the number of flip-flops required for designing this synchronous mod 6 counter. So for this we have to take this condition 2 power n greater than or equal to capital N, where the capital N denotes modulo value. So in this example mod 6 is there. So this 6 is the capital N value. So if you want to find this capital 6, that is because we have a condition 2 power n greater than or equal to n. So this 6 now applied a substitute in this capital N, and now we have to find the small n value. So when the small n value is substituted, if n is equal to 1, 2 power 1 greater than or equal to 6. Now this condition is not satisfied. Next we move the n value by 2 instead of 1. So 2 power 2 greater than or equal to 6. Now again 4 greater than or equal to 6 is not satisfied. Now we increase this n value by 1. So n is equal to 3. So 2 power 3 greater than or equal to 6. So now 8 greater than or equal to 6. The condition is satisfied. From this, the small n is taken as a number of flip-flops required to design this synchronous mod 6 counter for this example. So capital N value is 6, that is modulo value, and small n is the number of flip-flops required. So this is the excitation table for JK flip-flop. So Qn value and Qn plus 1 JK. Now Qn is the present state, Qn plus 1 is the next state, J and K are present inputs. Now these two values are equal to 0, 0. The J and K values are 0x, and Qn 0, Qn plus 1, 1. J value is 1 and K is x. That is don't care. Next 1, 0 and x1 is the combination. Next 1, 1, x0. Now this is the excitation table for JK flip-flop. By using this excitation table, we have to make the transition table. So this is the step 2. So in this step, we have to draw the present state in one column and the next state in next column. Flip-flop inputs are considered as third column. So in present state, we have taken 3 flip-flop in this example. So we can named as flip-flop A, B, C is the for this example, synchronous mod 6 counter. So the output of 3 flip-flops are denoted as next state, that is QA plus 1, QB plus 1, QC plus 1. So in this case, the present state values variables are QA, QB and QC. Now the present state conditions for 3 flip-flops A, B, C are denoted as QA, QB, QC, and next states are QA plus 1, QB plus 1, QC plus 1, and the flip-flops are denoted as JK, JB, JC. So in this example, in question itself clearly mentioned we have to use the clocked JK flip-flop. That's why we prefer this JK flip-flop here. In case instead of JK flip-flop, if the D flip-flop is chosen or SA flip-flop is choose. Likewise, the question has that the name, we have to choose that flip-flop. But in this case, JK flip-flop is there, so we have to make the excitation table for JK flip-flop and apply this value now. So now we have to consider only the first present state, that is first flip-flop present state variable QA and the next state of first flip-flop QA plus 1. So QA and QA plus 1 are combined 0 0. The corresponding input sequence JA and KA are 0 X. This can be determined from this excitation table. When 0 Qn 0, Qn plus 1 0, J 0, K 0. Similarly, here QA 0, QA plus 1 0. Our JA equal to 0 and KA equal to X. Next again 0, 0, 0 X is the JA and KA. Again our sequence 0, 0, so 0x. Next case QA is equal to 0, QA plus 1 is equal to 1. So now the excitation table condition is moved to next state, that is 0, 1. Now our J value is 1 and K value is X. Now this value is substitute here. This QA equal to 0, QA plus 1 is equal to 1. So the corresponding JA 1, KA X. Next 1, 1. Now what happened? The last state is occurred here. So Qn plus 1 both true or 1. Jx k 0. Now that condition is taken place. So Qa 1 and Qa plus 1 1. Our Ja is x and Ka is 0. And again 1 0 combination, that is third case. For this x1 is the input sequence. So 1 0 x1 is the sequence. Next case QA1 last, we don't have this condition. Why we put here the don't care condition? In this example, the question has mod 6 counter, that is synchronous mod 6 counter. So mod 6 is nothing but 6 states must present in the question. So that means 0, 1, 2, 3, 4, 5. Totally these 6 states to be considered for this designing of synchronous mod 6 counter. So remaining 2 states are not considered, are not present in this example. So for this case, the next state values are x, x, x. So before going to see this, we have to know how can we find this next state values. Because whenever the present state values are 0, 0, 0, the next state for the 0, 0 can be determined by the 0, 0, 1 of this next state. Now what happened? This value goes here. That is 0, 0, 0 is the present state. QA plus 1, QB plus 1, QC plus 1 means the next state of 0, 0, 0 is 0, 0, 1. So this move to this first place. And again 0, 0, 1 is the present state. The 0, 1, 0 is the next state. 0, 1, 0 is the present state. 0, 1, 1 is the next state. So this sequence of bits move to next state here. And again 0, 1, 1 is the present state. The corresponding next state values are 1, 0, 0. And 1, 0, 0 is the present state. The corresponding next state be 1, 0, 1. It moves here. Now 1, 0, 1 is there. The next state for this 1, 0, 1 present state is nothing but 0, 0, 0. Because this value will be the result. That is, we can mention the present state of 000 goes to next state for this 1, 0, 1 condition. Because in this example, we have only one, that is a mod 6 counter is there. So because of this condition, we must have a total 6 states in this example. So according to this condition, remaining 2 states are considered as a don't care. So based on this present state and next state values only, we can find this JA and KA, JB, KB, JC, KC. I have explained this JA, KA concept with this excitation table. Let's move to QB and QB plus 1. Now consider this 0 and this 0. Our sequence of JB, KB will be 0x. Next 0, 1. So in this case, again 0, 1 combination is there. So the following J, K excitation table values are 1x. Next 1 are compared. Corresponding result x0 and 1 0 x1 and 0 0 0 x. Again 0 0 0 x. Remaining two states are considered as a don't care case. And the last case QC and QC plus 1. So in this case 0 1 is there. For this JC and KC are 1x and 1 0 x1 0 1 1x 1 0 x1 0 1 1x 1 0 x1. Remaining two states are x. Now we have the flip-flop inputs JA, KA, JB, KB and JC, KC. Now from this inputs present state and next state QA, QA plus 1, QB, QB plus 1, QC, QC plus 1, we can find the value of JA, KA, JB, KB, etc. So for this we go for K-map simplification. So first we have to find the JA expression by using this K-map simplification method. So we have to consider this JA column. So in this column, what are the different values are present in this sequences that should be taken in this K-map. So for this, we have to consider this present state QA, QB, QC. Now these three are act as a input sequences QA, QB, QC and 0, 0, 0, 1, 1, 1, 1, 0. This is the four columns bits and 0 1 is a rows bits. So whenever you have a three variables, we have a three variable K map here. It consists of 2 rows and 4 columns. So totally 8 cells are present in this K map. Now we have to put these all individual column values in this K map. So now three values QA, QB, QC. These three are 0. The JA is 0. We have to put here. Again 0, 0, 1. The second 0 is there. We have to put here. And 0, 1, 0. The corresponding output JA is 0. So that is mentioned in this fourth row. First row, fourth column value. And 0, 1, 1. The corresponding result 1. Now 0, 1, 1. The value is 1. And next 1 0 0 x 1 0 1 x. For remaining all sequences has a x value, that is don't care condition. Put all those things. Now we can check whether octet mapping is possible or not. So there is no possibility to map in octet. Next, quad mapping also not possible. Next, we move to pair mapping. So these two, one and don't care can be considered as a single group, and we can map it as a dual map. So now the row values are cancelled and column values only considered. So the corresponding variables are QB and QC. That binary values are 1 1. So the expression will be JA is equal to QB into QC. So next we move for finding the Ka value. So now we have to consider this second column, that is Jk. Again we have to consider 0 0 0 and what is our output? X. So now we have to put X here and next 0 0 1 X is the next output. Again 0 1 0 X. 0 1 1 X. 1 0 0 result is 0. 1 0 1 answer 1. Now we have to put this 1 in this particular cell. And 110x, 111x. So now we can map all these 4 in a single group, that is quad map. So now this quad map can be considered. And for this we have to cancel this row values and consider only columns, second and third column. In this second column, first bit and say third column, first bits are alternate values 0 and 1 for QB. So we cancelled it and we have to take only this common binary values 1 1. So QC is your variable. So KA is equal to QC. Similarly, we go for JB. So in this JB, when QA, QB, QC 3 are 0, the output is 0. That is JB is equal to 0. So here 0. And J0, 0, 1. JB value is 1. Now we can put here. And 0, 1, 0 sequence X. 0, 1, 1 X. Next 1, 0, 0. our JB value is 0. So here we have a 0 and 101 also 0. So here put a 0 and remaining two values x. So now we can consider these two values in a single group, that is dual mapping is considered. So now we have to take first row and second and third column for comparison. First row variable is QA, the corresponding binary value is 0. So it is in the SOP method. So we have to take this 0 should be represented as bar value, that is QA bar is the expression for this particular 0. And now we have to compare these two columns. So in this QC variable values are same 1 1. So that is taken as QC. So QA bar QC is the answer for JB. Similarly, we go for KB, and in this expression KB for 000x, 001x, 0111, 0100, remaining all are 1. So again we have to map it as a doing a code map, quad map for this particular rows and columns. So the row variables are cancelled. We have to consider only column values. So QC is the answer for this particular expression. Because the QB values are alternate values here 0 and 1. So we can't able to take this QB variable. So we have to consider only the same value QC variable here. So next JC. So in this JC again 000 answer is 1. 001x, 0101, 00011x. So these all values should be placed in this. So all x, that is don't care, and ones are combined together and make it as a single group, and the object mapping can be done here. So from this the entire variables are cancelled. So final value for JC is equal to 1. Similarly for KC again we have to fill all the values present in the KC column. So now again the entire 8 cells are combined together and make it as a octet mapping. So final the KC value is equal to 1. Because there is no possibility to group all the individual, that is we can't write any variable name here because all the cells are mapped now. So the final answer is KC equal to 1. Now we have a variable JA, KA, JB, KB, JC, KC. That is, these are the inputs which is given to the flip-flop. So now we have to design a synchronous mod 6 counter. This is the step 5. So in this case we have a 3 flip-flop. The flip-flop names are assigned as already A, B, C. So that is mentioned in circle A, B, C. So the first flip-flop input is JA and KA. Second flip-flop inputs are JB, KB. Third flip-flop inputs are JC, KC. Now the output of first flip-flop QA, next QA plus 1, QB, QB plus 1, QC, QC plus 1. Now what happened? We have to consider this value here. So now the JA equal to QB into QC. So QB output is taken as one input and QC output is taken as one input. Both are added together. That is the that output is sent to JA. So apart from this, we have to give a synchronous clock pulse. That is, each and every flip-flop A, B, C has a common clock pulse. So uniquely we connect all individual flip-flops are in a same clock pulse. So it is called as a synchronous clock pulse, or simply we can say synchronous counter. And the first flip-flop inputs JA, which is equal to QB into QC. Apart from this, the out KA is equal to QC. So now the KA is connected with the QC result. QC result now it is connected with KA. And now the JB value is equal to QA bar into QC. Now the JB result is QA bar. So the first output invert value is taken as one input and QC is another input. Now both are joined together, that is AND together with the help of AND gate, and that result is sent to the input for JB, and KB answer is QC. So directly we take this QC as one input for JB. And JB, KB is here, and output of QB is already we have taken. So apart from this, we have to consider JC and KC. These two values are equal to 1. So simply we can make it as logic 1 because the value is equal to 1. So logic 1, which is nothing but plus 5 volt. So it is the input for this JC and KC. QC already we have connected with remaining all input sequences. So this is the design of synchronous counter. So the name of synchronous counter is mod 6 counter. So for this case we have to take 3 flip-flop. Already we have explained all those things. So with the help of these 3 flip-flops we have designed the mod 6 synchronous counter, and we consider the JK flip-flop. So because it is mentioned in the question itself. So this is the design procedure for synchronous mod 6 counter with the help of JK flip-flop explanation. I hope everyone understands this concept. Kindly subscribe my channel. If you have any doubt, you can ask me at any time. Thank you all.